Let's start with Murilo, who will tell us about the ALP searches possibilities using heavy ions and using the LHCb detector. Murilo, the floor is yours now.
I'd like to thank the organizers for the invitation. It's a pleasure here to discuss this possibility to search for ALPs at the LHCb. So I will focus on the ALP searches in heavy ions, but I just wanted to make sure that you are aware that LHCb has been searching for exotic states like long-lived particles, and you can check this in our publications if you like. Maybe I can share also my. So so what I'm going to discuss is these opportunities for ALP search at LHCb, and then I will present an experiment overview and the prospects for these searches, which unfortunately they're not yet finished, but there are some phenomenological results on that I'm going to show. So that's not a very long talk actually, but so there are studies that propose that ALPs can be well, that we can search for ALPs in PP collisions at LHCb. We have searches for ES to gamma gamma, and then if you tune the search with a similar trigger and similar strategies, you can search for ALPs, and there are already ongoing studies for that. But what I'm going to discuss is in heavy ion collisions, as we already saw in this workshop, if the ALPs if they couple only with photons with this Lagrangian, then we can reach good limit. I mean, can reach sensitive limits for this hypothetical new particle. So just to the overview is that if we have this a hypothetical particle that couple with photons, then we can observe them in lead collisions. LHCb can play a role, but we know that CMS and Atlas for the data that were already collected have 10 times more data. So what we are exploring is how LHCb can be complementary, and then of course, as I'm going to show, what we can try to do best is to go to lower masses, and as it was already presented, CMS published limits down to 5 GeV and Atlas down to 6 GeV, and then we are trying to go below this threshold. That's a reminder what is the LHCb detector. So we have the collisions taking place in this red spot, and the detector was fully instrumented in the forward direction. So that's a general purpose detector with forward acceptance. So of course it was designed for heavy flavor physics, but we do exploit the detector to do general purpose physics, and then we have a vertex locator that is a tracking detector that is able to measure IP resolution around 20 micrometers, and then we can have secondary vertices, but this actually detector that I'm going to discuss that we can use to select very clean collisions, even in the backward region that I'm going to discuss. And also we have the calorimeters here in the blue part that I'm going to discuss a little bit more for the photon. We collected in run 2 PLED and LED data, and this is the summary of what we call collider mode, where we collect the collisions between the beams, and the fixed target mode, where we inject gas through a smoke system, through a system that we call smoke, and then we actually have fixed target mode. I'm not going to discuss the fixed target mode, but I think that's also very interesting if you are maybe in a model that is in a very specific kinematic region that this particle is produced. It might be that the fixed target collisions, the model can be sorted with more sensitivity. So what I told you before is that this vertex locator detector, which surrounds the beam interaction, the beam interaction, so it can go very close to the beam, and as you can see that it has both backward and forward and acceptance. That's the only backward acceptance we have in the whole experiment, the detector. Actually, we have the Herschel that I'm going to discuss too. But what I'm showing is that if you have a backward track, even we get a straight line, and that's not going through all the detector systems, right? That's just going away. But we can do veto on these additional backward tracks and select clean collisions using the backward collision. That's very important for the kind of physics I'm going to discuss, and then we already done that before. In addition to this backward acceptance, we also have the what we call Herschel high rapidity shower counters for LHCb, and they were actually installed at the end of 2014, and we took data with these detectors and working, and they have 5 stations. You see the LHCb here in the red part. Of course, this is not on scale, but well, the LHCb is just the location. And then you have in the backward region, you have these 3 stations. In the forward region, you have these 2 stations. And then you can veto on particles that hit these detectors. And this you can see, for instance, the typical pseudo rapidity for a parent particle that produces hits in or energy depositions in these detectors or scintillators. At the end, what we have is that LHCb, as I told you, considering the VLO as a backward acceptance, where we can fit on these extra tracks, we have this green band for LHCb acceptance. And considering the Herschel, we have the pink band, while blue we cannot measure, we cannot see. So if you look at a typical collision or non-inelastic collision, that would be the distribution of particle density. In a single diffraction and double diffractions, SEP elastic and SEP inelastic, that's how we call it here. But you see that if we can actually see, we can actually veto on these extra particles with the backward and the Herschel detectors. I'm not going to discuss the very clean collisions results on very clean collisions, but I list here. So we have a few, I mean, most of them are in PP, but we have one result in lead-lead that is still conference here, but we're working on the paper. And now I discussed we can do very clean collisions, so we can select events with very low multiplicity or very low particle multiplicity. But then what about the photons? Then I'm going to show here, I decided to show a study that was done for PLED. Of course, we have studies for lead-lead that I don't have public plots, but for public plots, we have these studies for PLED using photons from simulation. And what's going on here is that we can see of course, okay, I could show the direct photon production. You can see in this reference called LHCb figure. So they have the direct photon production, but I'm more interested in photons from particle decays. So you can see here, for instance, the pi0 and eta, and it depends on the kinematic region. You can have different distributions, relative distribution for these, and using these decays that of course you conform with simulation, you can calculate the efficiency for the photons. So first you can calculate the acceptance, so how many photons you actually have hits in the calorimeter, and that's very high. And then then you have how many photons reaching equal, and then at the end you can actually have the photon reconstruction, what's shown in red. So what actually matters is the product of the three curves here, which is black. It's what we actually reconstruct, and what we and the denominator is all the photons in the LHCb acceptance, and that's around 40%. And I have to say that these events are very busy for PLED. They are generated with EPOS and PIFA. And it was also shown that if you reduce the surround activity, this efficiency can increase by a reasonable factor, and that's something we are working on. And also in the data, we had a low multiplicity trigger with a single photon where the ET threshold is around 1 TeV. So this day we have this data. So what we have done first was to study with event generators what is the actual acceptance for light by light, double diffractive production, and the QCD induced, called here QCD induced, but it's the gluon to gamma gamma. And what we see is that after you apply all the cuts that are showing here in this line, I guess you see my mouse, where we see light by light 616 nanobarms, you have quite low quite low QCD induced diphoton. So it's sizable, but it's very small. Double diffractive is basically vetoed by Herschel and the exclusivity cuts, and we still keep and of course with the even if the axion is a central like light by light, they both have they're more well. Even these two productions, we can see a sizable cross section in the forward direction. And of course, there is this electron background where we could mis-ID an electron by a photon. And then here we assume 0.5% of mis-ID, which is a baseline. And what happens is that even with the dielectron is actually higher than is expected to be higher than the QCD induced. If I look here, the fault selection, so I get 616 and then 87.5. But which is still lower compared to the ALP cross-section you expect for different couplings. But what's more important is how the limits can be improved. So here I showed the ALP masses for 2, 3, 4, 5. That's what for forward production, that's what we focused here. And then because we don't have any collider, we don't have any LHC limits in this region. So if we use this naive, this phenomenological study, we could read limits with much more sensitive to the current upper limits, and then extend the CMS and atlas limits, the current CMS and atlas limits for low masses. That's for lead with the data we have in black, and there are some prospects for run 2, run 3 plus run 4, and that depends. Maybe we are a bit optimistic here in the blue with respect to the luminosity, but okay, we still have to see how much luminosity we are going to get. And also here we did for PLED, and actually for PLED we do expect also be more sensitive to the current limits. So that's something we should look into in the data. And to conclude, we have the data with single photon trigger and low multiplicity events. I didn't show as much detail as other colleagues here, but we can discuss that in the questions. But the thing is that the reconstruction that the L0 trigger line that we have can reach quite low threshold for transverse energy, and that's a single photon trigger. And we hope that the current limits can be improved for masses below 5 TeV. So thanks for your attention.
Thank you, Murilo. I have myself questions, but let's see first if anybody raises the hand. Questions. The first one is, what is the maybe if Roderick is still around, you assume 0.2 inverse nanobar. What do you expect in PLED? In principle, what is the integrated luminosity at LHCb that you expect?
For round 3 plus round 4, or you mean?
I'm asking per year, and then we scale it. How many?
So 0.2 is what we have right now.
I've seen.
Yeah, and for round 3 plus round 4, that depends where you look at. Actually, I took so I use this as I think this is already not updated anymore, because from the talk we had before, I think LHCb was 2 inverse nanobar only for round 3 plus round 4, and here there is a additional 4, which I don't, maybe this was okay. So, but I would say between 2 and 4 for round 3 plus round 4.
Okay, and the second question. Sorry, yes, go ahead. Yes.
Yeah, just a comment. What we assume from the machine side is the request of 2 inverse nanobar for round 3 and round 4 together. This is what we're trying to achieve with these new machine scenarios, which we could So if you have 4 runs and we get about half inverse nanobond per run, we can just about fulfill that. But 4 we don't really get in the present scenarios.
Okay, this is something to follow up because only LHCb has possibilities here. Maybe at least 2, but LHCb, that would be a good reason for LHCb to fight for a higher delivered Lumi at interaction point. But of course, it always, I mean, it's the, I mean, we heard from Roderick the difficulties of achieving, of making happy everybody, all the interaction points at the same time, in terms of the luminosity. And the second question is, what about resolution of photons between in this region of masses of 2 to 5 GeV? Because here you will be dealing, as I asked before to Atlas colleagues, we will be dealing with a huge background from diphoton decays, from pseudoscalars, scalars, tensor resonances. So you will have many peaks from hadrons. So what is the expected resolution? Can you remove those peaks? How do you,
yeah.
You only
sorry.
Yes, you only discuss the continuum, and actually you mostly discuss the dielectron continuum, but you have, of course, light by light continuum plus all the peaks from all the hadronic resonances. So I was wondering what the photon energy and diphoton mass resolution is between 2 and 5 GeV in LHCb. Do you know this?
Yes. Yeah. Well, we don't have a public number to show, but it's around 3%. So 3 to 5, I would say 3 to 5 most.
Okay.
And I agree with you that I should have discussed also the resonances, and this is also something that it's not, I guess, very easy to calculate. But from my knowledge, from 2 to 5, it's not very clear we are going to have many resonances or in strong peaks.
Well, I mean, you will have the diphoton peaks from all the Charmonia already, starting at 2.9 with the, you have all the KC0, KC2, you have the
but the production
the
rate,
ETA-S, the production rates are as those will be peaks on top of the diphoton continuum. So
no, you mean I mean the production rates of this charmonium in exclusive events, right? So once you have only 2 photons in the detector, so you're basically looking at maybe charmonium that was produced in an exclusive production, and I think that involves some QCD induced.
no, I mean, setting aside QCD induced, you have gamma going to KC1, gamma going to KC2, so 2.9.
Oh yeah, okay. So this
2.9, 3.6, KC0, 3.4, KC2, 3.55. All those are CP even diphoton resonances that will be there. And actually, that's an interesting thing because you can determine the maybe with, in some cases, that diphoton width, for example, for the KC2S is very badly known. So if you do a measurement of this sort, what I'm trying to tell you is that you will have many peaks, and you can have also nice Charmonium physics. And this is only above 2.9 GeV, 2.9 to 4 GeV. But then below this, you have all the light quark pseudoscalar and tensor resonances that will be produced like the ALP. So this, you have basically Primakov production. Gamma going to a hadron that decays back to gamma, and this, you will have many of those. So that's why, well, but you say 3 to 5% resolution. That's not bad. That's not bad. So
yeah. So I'm going to send you maybe by chat. There is a paper that calculates, for instance, this charmonium cross sections, and they are quite small. But I agree with you that if you that's something to be in mind. I mean, to keep in mind. At the moment, we didn't really we didn't care too much, but because we think it is.
Yeah, I can tell you, we are preparing a paper. It's going to be out in a few weeks. I can tell you the cross sections for KC1S going to, so gamma gamma going to KC going to gamma gamma is 60 nanobarns. For KC2 is 15 nanobarns. For sorry, eta C, sorry, 60 nanobarns. Eta C2 15 nanobarns. KC0 20 nanobarns. KC2 30 nanobarns.
Okay.
So
okay.
this is not small. Live by light is huge. Is microbarns. I mean, integrated over this mass region. But of course, the continuum you don't care because you can fit it out and then you just look at the peaks. But what I'm telling you is that you, I mean, yes, I mean I'm looking forward to LHCb doing this. I think there are very nice measurements to do, but you will have many peaks to deal with. So that's why the better the resolution you have, the better will be to remove any.
So if possible, if you can also calculate these cross sections in the forward acceptance, because this is very, very useful for us.
Yes, we can definitely. Yes.
Because that's what I'm wondering, how these cross sections when you integrate over this forward region, and then we see
yes, absolutely. We have the numbers. We can discuss offline.
Okay, great. Thank you.
Ivona has a question.
Yeah, hello. Can I add something to that? Basically, there is a very, very detailed calculation of cross-section of those all resonances for low masses, and that results also for the LHCb collaboration have been injected into the yellow report. You were somewhere in your presentation, you were referring to the yellow report numbers, right? So you can basically find some projections precisely done for the LHCb.
Yes. I know what I'm talking about, but that's why I think from using these numbers that I didn't put here in the slides, but we discussed that this is quite small because it was
not really. It goes in line with what David was discussing before, right?
Yeah, but look at the numbers for light by light, and you see that it's even after going for forward selection, we have 600 nanobars, and the signal is like 900 nanobars. So if you have a fully integrated something,
you have numbers for light by light, but I'm referring, to resonances decaying to the diphoton state, right? And for that, I believe you don't have numbers in this presentation, and they become really significant in the low mass region, which you aim for in your measurements. Okay, I will send you perhaps a link to that calculation.
Sure. Thanks.
Sorry, I was muted. Anybody else wants to ask any question to Murilo? If not, let's thank Murilo and move to the next talk.